My report is all about program example, but first, let me introduce the Motorola 68000 processors. Has 80 registers that are directly accessible users. Those are the 8 general purpose data registers, number from D0 to D7. The second is 8 address registers, number from 80 to 87. The third is 1 program counter or PC or the 32 bytes. And the last is 1 status registers or SR or the 16 bits is divided into two parts. The first is system byte, can be seen and accessed only by the operating system. And the second is condition code register, which is CCR, can be accessed by the users.
So we have here program examples of linked list insertion and deletion subroutine. So here in linked list, each record contains an address value in one-word linked field that specifies the location of the next record in order to enable connecting the blocks together to form the ordered list. So here linked list insertion subroutine. So compare address long word 0 into A0. A0 is our head. So if branch greater than 0, proceed to head. And if not, branches ignored. So move address long word. So insertion subroutine assumes that the ID number of the new record does not match that of any record already in the list. So we will now proceed to deletion subroutine. So here, compare long word R head to R ID. The given is the R ID number. So if branch greater than 0, we'll proceed to search. Then if not, branches ignored. Then move address long word R head plus 4 to R head. And here, we delete the head fragment. So return to subroutine. So compare again. Long word A0 into D1. So here, branch is greater than 0, they will proceed here. So move address long word R head into R prime. A2 is on R prime. So move address long word R prime plus 4 into R next. Then compare long word R next into R ID. So here, if branches equal, this will proceed to delete. So if not, let me address long word R next to R current. Then branch hook. Move AL long word A2 plus 4 into A and compare long word A3 into D. And here, branch is equal to 0. So we'll move L A3 plus 4 into D2. D2 is our R. So move long word R times to R prime plus 4. Then here, we return to subroutine. So the deletion subroutine assumes that there exists a record in the list with an ID number that is not matched the contents of our ID.
So our next topic is registers and addressing modes. We're going to look at the role of registers in the CPU. These diagrams of the CPU are very much open to interpretation that the role of units might look like this. And if we were to draw a diagram and now we're going to extend that diagram, it is very simplistic portrayal of the CPU. We're going to extend it so that it includes these things called registers. First is the registers. So what is registers? It is a small memory space inside the processor. It can each hold only single values, are termed as special registers or general registers. The first registers we'll look at is the PC, the program counter which lives inside the control unit. Next, the program counter. It keeps a check on where the next instruction is in main memory, stores instruction in order, tells the processor control unit where the next instruction is that needs executing. It keeps a count of number of instructions that have been executed. And the total is incremented by 1 each time. By the control unit incremented means we add 1 more each time to that counter. So that's the program counter. Next is the MAR or memory address register. It temporarily stores the address of the next instruction that needs to be executed by the processor. Addresses are stored so the processor knows where in main memory to look for the instruction. Addresses are put into the MAR by the program counter, so that's how the program counter and the MAR are linked. See that arrow there portrays that. And the next one is the MDR or the memory data registers. Once an address is in the MAR, the processor can fetch the instruction from main memory and a copy of the instruction is put in the MDR. CIR or current instruction register. It stores a copy of the instruction currently in the MDR. The copied instruction is split into parts. One part is decoded by the processor ready for execution. The other part is the address of where the data is that needs to be used in the conjunction with the instruction. Because any instruction that the process is going to use and execute these data go with it, there's no point on having instruction if there is no data to go along inside, no data to be executed. In essence, the current instruction registers hold instruction that is currently being executed. And the last is accumulator. It stores any values that are needed as part of an arithmetic operation. The only general purpose register that we've been looked at. All of the rest are non-special registers. Next topic is about addressing modes. The operation field of an instruction specifies the operation to be performed. This operation will be executed on some data which is stored in computer registers or the main memory. Purpose of using addressing modes: to give the programming versatility to the user and to reduce the number of bits in addressing field of the instruction. There are different types of addressing modes. First is immediate mode. In this mode, the operand is specified in the instruction itself. An immediate mode instruction has an operand field rather than the address field. For example, add 7, which says add 7 to contents of accumulator. 7 is the operand here. Register mode. In this mode, the operand is stored in the register, and this register is present in the CPU. The instruction has the address of the register where the operand is stored. Next, register indirect mode. The instruction specifies the register whose contents give us the address of operand, which is in the memory. Thus, the register contains the address of operand rather than the operand itself. Next is the auto-increment or decrement mode. In this, the register is incremented or decremented after or before its value is used. Direct addressing mode. Effective address of operand is present in instruction. Single memory references to access data. No additional calculation to find the effective address of the operand. For example, add R1 4000. In this, the 4000 is effective address of the operand. Next, indirect addressing mode. The address field of instruction gives the address where the effective address is stored in memory. This slows down the execution, as this includes multiple memory looks up to find the operand. Next is displacement addressing mode. In this, the contents of the index register is added to the address part of the instruction to obtain the effective address of the operand. If EA equals to A plus R, in this the address field holds two values, A, which is the base values, and R, that holds the displacement, or vice versa. Relative addressing mode. It is the version of the displacement addressing mode. In this, the content of PC is added to address part of the instruction to obtain the effective address. If EA equals to A plus PC, where EA is the effective address and PC is the program counter. Next is the base register addressing mode. It is again a version of displacement addressing mode. This can be defined as EA equals to A plus R, where A is the displacement and R holds pointer to base address. And the last one is stack addressing mode. In this mode, operand is at the top of the stack. For example, add. This instruction will top 2 items from the stack and add items and will then push the result to the top of the stack.